Hey, ARE and CE 4260. Now we're going to talk about bars in compression. And once again, the code has significantly changed for 2019. I'm going to show you, I have every single ACI building code that there ever has been. This goes up to 2011, and I do have the most current 2014 and 19 here at home. These are in my office back in the engineering building. I got these codes from Charlie Dolan, and so Charlie, if you see this, thank you. Anyway, this lecture is based on the 2019 code. And this is the basic equation for the development length for bars in compression. And it's the greater of these two things. These are all what we've talked about before: the steel strength, the concrete strength, and the lightweight concrete factor. The only thing different is this psi r. And you take the least, the greater of these two things. And so this psi r, or confinement factor, it's either 1.0 or 0.5. You get to use the 0.75 for a shorter development length if the longitudinal steel, it's usually in a column when the steel is in compression. If it's enclosed in a spiral, circular helix tie with a diameter greater than 1/4 inch and a pitch of 4 inch. Number 4 bar or D40 wire ties, that's just square hoops or rectangular hoops, spaced less than 4 inches, or hoops with spacing less than 4 inch. Otherwise, you're going to use this 1.0. You get to reduce the development length if you have extra steel. So if you only needed 4.5 square inches, but you provided 5.0 square inches, for example, you could reduce your development length by 10%, because that comes out to 9/10. However, you're not allowed to do this reduction for these reasons. Okay, so any of these things happen and you cannot do that reduction I just talked about. Non-continuous supports, where you need the FY, where the bars must be continuous, if you have hooked or headed bars, or if you're in your seismic categories C, D, E, or F. Okay, we're going to finish our discussion by talking about splices. Sometimes you can't get a bar long enough for what you designed. I think the longest bar you can get is 60 feet. And that has to do with the length of a truck that can navigate off-ramps on a freeway. And so if you need a bar longer than that and you need to splice it, these are your options. You can have just overlap them. This is a mechanical connector. And this is a grouted connector. And so you have these options to splice, and there are two different kinds of splices. Let me see if we can get that here. Okay, so two kinds of splices, tension or compression, and there are some special requirements if you're splicing in a column. Before we talk about these kinds of splices, there's some rules we need to discuss. Okay, you cannot splice the two largest bars, number 14 and 18, and that's because we just don't have experiments and we have no data about those, and so we're not just going to extrapolate what we know about number 11s and down, so you cannot splice the 14s and 18s. However, you can splice the 14 and 18s if you're splicing them to smaller bars. That would be 11 or smaller. If you have a non-contact splice, like this picture right here, so you see, let me highlight that, this right here. So if you have that situation where you're splicing by overlapping but they're not actually touching, they need to be within 6 inches of each other. Okay, so non-contact splice, the bars need to be within 6 inches of the other. You cannot use the excess steel factor that you use in a compression I just talked about. You can't use that for LD. And if you have grade 80 or higher and the bars are less than 6 inches apart, you need confinement. You need to wrap that somehow. And again, there are special considerations for shotcrete. It's where you can put the steel up and you spray the concrete on there, and bundled bars, and you can read the code for those applications. Let's first talk now about tension splices. There are two classes. There's a Class A splice and a Class B splice. In a Class A, you have to splice them a development length. We talked about how to calculate the development length and tension. A Class B splice, you have to have an extra 30% overlap, so 1.3 development length for your splice length. And you are always a Class B unless these two things happen, then you can be a Class A. So you need to have twice as much steel as you need, and less than half of the steel is spliced. That sounds almost like the quote that Bilbo Baggins made at his farewell party, if you know what I'm talking about from The Hobbit. But anyways, to be a Class A splice, you have to have more than double the steel needed and less than half of that being spliced. Now, let's talk about compression splices. You can have a mechanical device where you put the two pieces together like this, and then it's wrapped with something. You could weld them together, maybe like this, and then like that, and then weld them, or you can just overlap them. If you have a mechanical or a weld, it must be able to develop 1.25 times the yield strength. And if you're using a mechanical device and you're trying to splice the bars together like this, these edges need to be flat so that they can touch. So I don't have anything round around here, it's my fingers, but this wouldn't work because the ends of my fingers are not flat. Okay? So they need to be square where they meet. You have to cut them. And it has to be within 1.5 degrees of 90 degrees, and the total gap can't be more than 3 degrees if you're 1.5 degrees off on both sides. And if you use mechanical devices, not only do they have to be cut flat like this, they have to be confined with hoops, ties, or spirals. Okay, what is the development length once you've for overlap? Okay, so sorry, these two we're talking about mechanical or weld. The third option is just overlap them like this. If you overlap them, if it's grade 60 or below, the overlap has to be 0.0005 Fy in PSI times the diameter of the bar, but not less than 12 inches. If you have grade 70 or 80, here's the equation here. And if you have above grade 80, it's the greater of these two things. The equation for grade 80, or the tensile splice length. That's interesting. And in all three cases, if F prime C is less than 3,000, if you have very weak concrete for some reason, you have to increase the splice length by 1/3. And again, this is compression splices. Now, I talked about not being able to splice number 14 and 18 bars. Move this down. You're not allowed to splice a 14 to a 14 or an 18 to an 18 or an 18 to a 14, but you can splice those larger bars to number 11 or smaller, and the splice length is the greater of the splice length for the 11, what we just talked about, those equations, or the development length of the number 18 or 14 bar, whichever is greater. So that is splicing for tension and compression, but there are some special rules for compression and tension for columns. And if you're splicing in a column in compression, which is normally, columns are in compression, move this away. The area of the ties in both directions has to be greater than 0.0015 H times S. And let me try to draw this. Okay, so you have a column that looks like this. And you have some bars that you're trying to splice. And you have a tie like this. And what you would do, this is a rectangle, so it has different heights, H1, H2. Okay, S is the spacing. And so this area, let me see if I can change the color. So, can't get that to maybe, okay, these two. So the area of those two, and the area of those two bars, okay, has to be greater than 0.0015 times this H times the spacing of the ties. Whereas the area of these two legs has to be greater than 0.0015 times this distance times the spacing of the ties. So in both directions, this has to be true. If you have spiral columns, and if you do have that true, you get to reduce the splice length by 0.83. Otherwise, you have to use the splice length we calculated earlier. For spiral columns, if you have minimum spirals, you can reduce the splice length by 25%. And in either case, the minimum splice length is 12 inches. Now, this next thing is a little mind-boggling. Columns can be in tension. So in earthquakes, a building can move back and forth like this. And on the, so, the building, let's see if I can do this. Yeah, it'll bend. It can bend backwards. Okay. Here, wait, there we go. So it can bend like this. And on the tension side of the building, those columns might be in tension. Also, in the Christchurch earthquake, I believe the second one, the vertical acceleration of the ground was more than 1g. So it was possible to make all the columns go in tension because it was greater than gravity. Anyway, even if the columns are in compression, they must have a minimal tension capacity just in case. And if they're in a little bit of tension, they might be class B or class A. And if they're in a lot of tension, it'll be a class B splice. Remember, that's the extra 30% length. And there are other considerations. This is beyond the scope of this class, but if you want to read more about this in the 2019 code, it's in section 10.7.5.2.2, as you see there. Okay, so that is the end of development length. And all of this, though, is just a small part of the big concept of cutting the rebars. Okay, so we'll now put everything in its context in the next two lectures.